guys giving lots of good feedback? No? So you guys are okay with everything, right?
Well, pretty much what you could say is we're not gonna see any changes till we go through it, so.
Well, yeah, it is, yeah. It's sort of like you guys are making changes for like the next group of people coming in. So, I mean, because think about it, the way it is right now is based on the people who came before you, right?
Well, so there was a complaint that we made that they said they had when they were in school, and that every class they've ever talked to has had, but they haven't changed it. These people are 6.
What is it?
The labs being 1 hour of being emotion work out of any of our classes. And they said it's the same way as when they were in school, but
yeah.
So they aren't going to make
The
changes.
same way when I was in school. Yeah, that's.
It is the same way when I was here.
Yes, interesting.
I just wanted to actually count for more in your GPA than just one credit.
Yeah, shit. I mean, because they can be really time consuming. Yeah.
Have 20% of your grade be due to ethics memos, which aren't supposed to be on the class.
And it's not just like regular homework. I mean, you guys are actually learning a few new things, in that lab. So I mean, did your lab come with a lecture as well? Yeah. See. Yeah. So yeah. I don't know. It's kind of weird. Okay, so yeah, so that's the IAB right here. So that sort of like changed a few things. So what we're going to do, like I said in email, our exam was right here on the 20th, but we're going to push it to the following week, but make it on a Friday still. Okay, so now it's going to be on the 27th. And so we're missing a lecture here. So what I'm going to do, these next 2 lectures, I'm going to finish up chapter 11. And so I'm going to cover pages 148 through 660 today. And then on Wednesday, go 661 through 669. And that's like the last part of that. This part right here, I think that gets into chapter 12. Yeah, this part's, chapter 12. So next lecture, the rest of 11, and then we're done. Now, fortunately, this part of the, these set of pages are, I was able to put it together like just 15 slides, as you can see, so it's not that bad. Yeah, and we'll have our practice exam on the upcoming weekend. And am I right in thinking that Sunday at 2 is still good for everyone? Because sometimes it changes. Like sometimes, yeah, I was available here, but I'm not available there. So it looks like it's good for everybody. So we'll still do it. Yeah, and then also it still gives you guys an entire week after taking this practice exam to find out what areas you need to brush up on, if there are any. So you have a week for that. Well, almost a week. Yeah. Okay. So for review on lecture 9, we went over the voltage transfer characteristic, right? And saying that this voltage offset right here that is in this range of microvolts to millivolts. Okay, we can model it like this, like adding on an element that is a voltage offset. And you can trim that with a potentiometer. And if you have a circuit, like in your lab, you can hook it up with your op amp and then add on a potentiometer and trim that voltage offset off by measuring it. Okay, so the last time we met, we talked about input bias and offset currents. Okay. And so we found out that if you have an op amp that's even, slightly less ideal, we find out that there's actually currents going in here into the op amp, very small currents, and these currents, they're actually going through the elements in there, and without that happening, the op amp wouldn't be able to function. So you have these bias currents, 1 and 2, and the manufacturer, we found out, will give you the magnitude of like the largest value, but they won't give you the direction. That depends on if it's PNP or NPN type. And this current offset is the difference between these two. The positive node, the non-inverting node, minus the inverting node. Okay. We also found out that there are some output error associated with these input currents. And on this picture, instead of having the currents pictured on the inside, which they are, the author moved them to the outside, but it's the same idea. Okay, but don't think that there's like actually currents going in this direction that account for these. These have been moved outside of the picture. Okay, and so one thing you could do to reduce that error we found was to add a resistor here. And if you choose the value of that resistor to be this value, you're able to minimize that with just one resistor. And the book also said that there's other methods too that can be employed, but they only talked about this one. We also looked at the effect of input bias and offset voltage. So here's some input bias right here being modeled, and offset voltage. And what can happen is if your circuit is on and just sitting there not doing anything, what can happen is that this capacitor could be fully charged. And this is an integrator, right? It'll be a differentiator if that was capacitance and that was resistance. Okay, but this is an integrator, and so what's going to happen is that charge is going to continually develop slowly because the offset voltage is very small typically, and this is really small, right? But what could happen is that this could saturate, and it's going to saturate to one of these values, either this one or this one, right? And so what you'll need to do in that case, that happens, if you have like a short circuit switch across a capacitor, you can toggle that immediately before you use it to unload the charge that's been built up. And we also talked about common mode rejection ratio. And remember, what that is that you have these two voltages here, but you could look at it as voltage actually going into here, right? And the voltage going in is the average of these two. Okay, so this VID is a differential input voltage. We've been dealing with that a lot, and that's just V1 minus V2. Okay, so the non-inverting minus inverting, V1 minus V2. This other one, the common mode input, that's the average of those two voltages. And so before we just looked at it like this, right? V out is just the amplitude, the gain of the amplifier itself multiplied by the voltage, the differential mode input voltage right there. But now we have this other term right here where it has its own gain, and this really small value is being multiplied by the gain, but this can be significant, right? And what you can do is you can factor out this gain right here, and if you factor out this gain, it just comes out with this, but this right here becomes this ratio right here, which is A over A common mode. Okay, so this is the common mode rejection ratio. Common mode rejection ratio. Okay, so the idea is to have, to have a system that has a really good value of that. So you can really reject that common mode voltage. All right, so we're going to cover these concepts today. So just 11, 13. Okay, it's all about the frequency and bandwidth of operational amplifiers. And we'll finish up looking at Nyquist, but we'll like do an intro to Nyquist, and then we'll get more into Nyquist on Wednesday. Okay, so we actually left off with these slides last time, right here, the frequency response and bandwidth. So each component within an op-amp has parasitic capacitance, which limits op-amp's bandwidth. And if you recall, do you remember what time constant was? Do you remember what that is in terms of RC? Hmm?
RC.
Is it RC or what of RC? Okay, so this time constant, do you remember what that meant? What this tau was?
Is that the discharge?
Yeah, but like if you were to plot it out, what does this represent in terms of a plot? Like for example, we know like if this is like the asymptotic value right here, you know, and you're starting right here, what's going to happen is that you like eventually get up there and then it'll asymptote to that value. Or if you're up here and you want to get down to this value, you'll start right here and then you'll asymptote, you know, to this value down here, right? And so you eventually get there close enough that you'll call it that value in either case. But what does that mean though? That value of tau? Hmm? You guys remember?
Isn't it like a certain percentage it takes to get to
Yeah.
part of the graph?
Yeah, exactly. You remember that percentage?
9 something? 60 something?
Well, it was like,
1 to 2.
I think it was like,
It's e to the negative.
it was like 30 something or 60 something.
There we go.
It's e to the negative 1, which is 63% or 37%.
There you go. Yeah. Yeah. So this right here, e to negative 1, and that came from being e over t divided by tau, right? And so whenever t was equal to tau, that is 1. And then e to negative 1 power, what was that? 33%? 37%? Okay, so every tau, like if t was tau, that's 1/37%. If t was 2 tau, then it'll be like 37 times 37. If t was 3 of these taus, you know, time, it'll be 37% of 37% of 37%. So you're getting closer and closer to whatever asymptotic value. So the rate down here was like you're just multiplying by 37%. Up here is like 1 minus 37%. You know, going up that direction. But anyway, so what that means is that your systems, when they turn on, or when a signal is going into an op-amp, you have these, each component has this tau associated with it because it has a little bit of capacitance. Every single element has some type of effective resistance, some type of effective capacitance. So you have this tau, and you have an overall tau because you have many components in there, right? But you're never going to get something that just like cuts on and then straight over like that. I mean, it's not going to look like a step function, like a step function. It's never going to look like that. Now you can have like, you know, a really nice one where it's a little closer to almost being immediate, but you're not going to get there with these analog types of systems because you always have this parasitic capacitance. Okay, but that's where that's from. Okay, so now these general purpose op amps have this low pass character, where you have high gain at DC and single pole response. Okay, so it looks like this. It takes this form. Okay, and that's the overall character of it. Okay, and so if you look at that right there, you know, based on what we've been dealing with, you can see that it has you know, this DC part right here, right? Because this is like an enumerator. So if you did like the 20 log of that, you would just have this value. In this case, it's at 80 decibels, and then it's divided by this, so it would be minus 20 log of whatever the denominator is, and that's where you get the fall off after that. Okay, so very simple: DC and then fall off, DC and fall off. Okay. Now, this piece right here is like the maximum value. This A0 is this up here. Here's A0. Here's omega B. Omega B. So A0 is the open loop gain. And remember what open loop means. Excuse me. Omega B is the bandwidth of that. So since it's low pass, the bandwidth goes from 0 all the way to cutoff. That's the so the cutoff is the bandwidth for low pass. Okay, if it's band pass, it's a little different, and we have a band pass in lecture day 2. Okay, so that's what omega B is, and remember that right there is when it's 3 decibels down, negative 3 decibels. So, for example, if you put if omega happen to be omega B, this fraction will be 1, so you have a square root of 2, and 20 log square root of 2 is what? 3, yeah. And because you're dividing by it, you know, it's going to be the negative 3, right? If this was in the numerator, it would be positive 3. If you're dividing by it, then negative 3. Okay, so now this omega t, which is equal to this right here, this is called the unity gain frequency, or the gain bandwidth product, and it's the frequency at which this right here, the magnitude of that equals 1, or 0 decibels. Okay, so here's 0 decibels. This whole red line right here is your transfer function, the magnitude of that in your varying frequency. So when the frequency at which this crosses 0 decibels right here, that is omega t, and that is the unity gain frequency. Okay, that's 0 decibels or 1. Okay. So we'll go back to these. Throughout the lecture, we'll come up with these terms again. Omega B, what A0 means, and also this unity gain frequency. So keep in mind what these are, because we'll come back to that in the lecture for other things. It's not acting right today.
So they need new batteries?
That's what I was thinking, but when I went to the laptop and I pressed the arrow buttons on the laptop, it still did not work.
Oh.
So there's something else going on. It's not the battery. I like to reboot it. Yeah, why didn't I just reboot it? Because it looks like the one had a problem again. This laptop reboots okay. It's not too long. I just hope there's no updates.
Is that the first Wednesday of every month? Is when they push those out?
Hmm?
I think they only pushed us out the first Wednesday.
What?
The Windows update.
Oh, really?
Yeah, I think that,
Oh.
it's definitely on the schedule. It's the
I didn't know
first,
that.
the first day. I think it's Wednesday
Mhm.
of every month.
Okay. That's good to know, because we have class on Wednesday. Yeah. I remember rooting before I get to class.
And you don't wanna look up.
Let me look at that.
Yeah, see, it didn't take that long. I just gotta.
Oh, Tuesday. Sorry, first Tuesday of every month.
Oh, Tuesday?
Yeah.
That's even better for us.
Because it's only Wikipedia page. Hatch Tuesday.
Okay, yeah, so, so we were here. Okay, so here. Okay, so this transfer function at high frequencies and gain bandwidth product. Okay, so, so at high frequencies, when omega is much greater than this omega b, which is right here, which is the cutoff frequency, and also the bandwidth for low pass, okay, what happens is that this function right here for this value, becoming really large, is being added to something really small. So basically, what's inside the square root is this omega squared, that just becomes omega. And remember, A0 times omega b is just omega t from right here, the unity gain frequency. So it's just omega t over omega for high frequency. So the gain bandwidth product right here is this magnitude times omega. And so at high frequencies, you could just say that this value right here is omega t, right, over omega, then times omega, so it's just omega t. So it's just the gain bandwidth product is just omega t, and that's the frequency at which this function right here, the transfer function becomes unity at 0 decibels. Okay, the gain bandwidth product. And then, yeah. Okay, so let's look at the frequency response for non-inverting, and then we'll look at the one for inverting. So we'll do non-inverting first. Okay, so remember the two alpha amps. One is an inverting op amp. I know it's kind of tiny, but inverting op amp. Other is non-inverting. And as you see here, for the non-inverting op amp, you have the positive node here, the negative node here. So the non-inverting and inverting, and then that feedback loop is going into the inverting, and the input is going into the non-inverting. For the inverting op amp, the feedback loop is going into the inverting node. Okay, and here's the gains, the V out over V in. For the inverting op amp, it's just the feedback over the input, so negative RF over RN. And for the non-inverting, it is 1 plus RF over RN, so feedback over RN, which you have this 1 plus in front of that. Okay, and yeah. So, so as a point of clarity that I'm, still trying to understand a little bit, is that even though this op amp is an inverting op amp, this is a non-inverting op amp, both of the feedbacks are negative. So they both have negative feedback. Okay, and if you have negative feedback, that is the thing that makes it stable. Okay, so both of these are stable, but this one just is non-inverting, so the output is the same phase as the input. Here's inverting, so this is 180 degrees out of phase, that negative right there. But both feedbacks are negative. Okay? Yeah. Okay, so for this closed loop feedback amplifier, so we found out before that we can model like this right here, which is just A over 1 plus A beta. And remember that this was this T, which is the loop gain. So AV is the output over input of the amplifier, and A alone is just the amplitude, the gain of the amplifier, the op amp in here. Beta is the gain of the feedback. Okay. Now we found out that these amplifiers are like low pass, so we could take this A right here and plug in what we know the behavior of these low pass filters are, right? And then if we divide top and bottom by S plus omega B, we come up with this expression right here. And then we can simplify it even further by dividing top and bottom by this 1 plus A0 beta right here. Now, so this right here. And so this expression right here is just like this, but at 0 frequency. So that's what you're getting right here. That's what you're starting off with. So we can relate this expression to this at 0 frequency. And this expression right here becomes this, where you can recognize that this omega H is this expression right here. And just this right here. So this is the upper cutoff frequency. That's what the book is calling it. And okay, so they're cutting off. They have the word cutoff right here. Of course, we've been recognizing that cutoff has to do with 3 decibels down, right, for voltage and current, because that's the square root of 2. If it was power, it would be 2, not square root of 2. But they're making the distinction that this upper cutoff frequency is the frequency at which this value right here, so if you were just to plot this right here, that would be this frequency right here. Okay, and yeah, so here's the value at A0. Here's this right here in blue. So here's this H, this omega H, this upper frequency, and this value right here is 1 over beta. And if you multiply both of these together, A times beta is 1. Okay. Also recognize this, that the loop gain is A beta, and if you're going to do this in decibels, it's really A minus 1 over beta. So it's sort of like this is just a difference between the two. So this value is a constant, right? And so if you were to plot this, and then you subtract it from this line, the difference between that would be the value of your loop gain, which is kind of interesting. For A0 beta being much, much greater than 1, this right here is about equal to 1 over beta. And also omega H is about equal to beta omega T. So that's for the non-inverting. For the inverting op amp, so let's do it like this, where we've seen this before. You have the ideal multiplied by this factor, which is the loop gain over 1 plus loop gain, right? And we can substitute in AS for both of those. If you look at the differences between how we're representing this and how we're representing this right here, you see that we're absent the beta here. But over here we have the beta in that. Okay. So and of course here you see that the ideal is the R2 over R1, and in this case for the inverting, that would be R2, that would be R1. That's where that goes right there. That's just another way to model it. But for this being much greater than 1, you can approximate it with this, and where omega H is equal to beta omega T again. So in summary, for the non-inverting amplifier and the inverting amplifier, our beta is still the same as R1 over R1 plus R2 for both of these feedback loops right here. On the DC gain, slightly different. So we know this right here. I mean, these are like our ideal amplifier at 0 frequency. The feedback factor for beta is different for these two. The bandwidth right here is the expressions are the same, even though the betas are different. And for the input resistance, we have a common mode in parallel with the differential right here. And for this right here, we have this as the input resistance. For the output resistance, they look the same kind of form, even though the values of beta are different. Okay. All right, so let's look at feedback control of the frequency response. So, so we've seen this before, where here's like the typical response of a general purpose type of amplifier, but now we're going to make this AS right here equal to this. Okay, so it's a little more complicated, and in doing so, we have this upper frequency to worry about and this lower frequency. So, so right here we have the upper frequency and lower frequency. So this is like, you know, a mid-band type of band pass type of response for this. Okay. And so if you do some mathematical reduction, it'll come out to be this right here. And so what you see, and now why this is called feedback control of the frequency response, is because you can see here where the difference between this closed loop amplifier and the open loop amplifier, you know, you see this as a function of beta right here. So looking at that, you know, you do have some control over, you know, I suppose the slopes of those. And also the distance between the two right here. You see a beta involved in that right there. So beta does have an effect on the frequency response in terms of the slope and also heights between the open loop and closed loop amplifier version. Okay, so let's move on to slew rate. So slew rate is the maximum rate of change. So it's like some type of derivative with respect to time, right, of voltage at the output of the op amp. Typical values of the slew rate range from 0.1 volts per millisecond to 10 volts per. Oh, I think those are. I don't think that's a millisecond. I think that should be in the Greek symbol. I think it's supposed to be micro. I'll double check that. Yeah, so I think it's 0.1 volts per microsecond and 10 volts per microsecond. Okay, so for a given frequency, slew rate limits the maximum signal amplitude that can be amplified without distortion. And what we were talking about before has a lot to do with slew rate too, right? So here's the input. This is a typical sine wave. And the thicker version is the output. It has a different amplitude, but you can see it has the same frequency. But as you can see how it's starting off, it doesn't start off sharp like this. It's sort of like starts off like here and then starts climbing up, right? And that's all due to the slew rate. So if this is your input right here, I'm sorry. Here's your output right here of this sine wave. This maximum value right here is like the like that. Okay, so what I'm trying to say is, if you want to get your maximum rate of change, you take this right here, divide it by 2, and look at that maximum value. And the maximum value is, of course, when it crosses the 0 right here, right? So here's like this, the largest slope. After that, the slope, you know, begins to get smaller, and then approach 0 at the extremes. Okay, so that's that right there. So you get a value of omega m right here times omega. Okay, so that's the slew rate for that. For full power bandwidth, that's Fm, is is the highest frequency at which full-scale signal can be developed. And so what full-scale means is just, whatever the largest value of voltage is coming in, right, that can be developed. And that full power bandwidth is this slew rate divided by 2 pi over 2 pi times VFS. Okay, so now let's turn to looking at macro models for op amps and look at the frequency response. So typically inside of an op amp, there are lots of bipolar and field effect transistors, right? Anywhere from 20 to 100 of them. And so when you use a tool like SPICE, it doesn't really model all the components individually. I mean, you can do that, but what they try to do is make a macro model to make a faster type of response. Otherwise, a lot of simulations would be, a whole lot slower. So this is how they model that. So, it's a 2-port, right? And so what they do is they model what goes on in an op amp when you're looking at frequency response. You have the, some effective R and effective C. Okay, so here's going to be your RC time constant. And you're able to choose what these values are. What is the effective R and effective C of your op amp. So as you see here, you have this voltage across here, and that voltage controls this. So here's our voltage controlled voltage source, and that's attached to this RC. Now the voltage across this is controlling this. So that gets amplified, right? So there's like some kind of Thevenin type of part coming out right here. Here's your output. Okay. So it's here, it says here that simplified circuit representations are available in most situations. Most simulators to model the terminal behavior of op amps that include all 9 ideal limitations of op amps and a large number of parameters that can be adjusted to model the op amp behavior. To model a single pole roll-off, like what we've been doing, an auxiliary dummy loop voltage controlled voltage source V1 in series with R and C right here is added to the original 2-port model. The RC product is chosen to give the desired 3 decibel point for the open loop amplifier. Okay, so so basically you're choosing this RC. You're choosing your beta to be based on RC. Now, and I'll tell you exactly what these values are to choose your frequency for your low pass bandwidth value. Okay, so here are the typical parameters of a macro model inside some tool like SPICE. So it has many other things too, not just R and C, but you can set all these things, but it's a macro model. So they're not modeling all the circuit components, they're just making models like this. This piece right here is just for the RC, but they have other things in there that model these other things too. So it behaves like a real amplifier, even though it's not modeling all the circuits. Okay. Oh yeah, and you can see here's the N or P type. This determines remember the direction flow of the bias currents, right? Slew rate. Yeah, okay. Yes, these microseconds. Yeah. Okay, so so here's like an intro to Nyquist, which has to do with the feedback amp stability. So this is the intro, but we'll get into more in next lecture. So basically, we've been modeling things like this, right? And this has been A beta down here. So this can become unstable when you have a pole here. Okay, so this becomes a pole. Well, like, what does T have to be for this to be a pole? We have a 1 here. Yeah, -1, exactly. Exactly. So whenever this open loop gain is -1, then you have a pole, then your system is unstable. Okay, so it says here, if gain AV of the amplifier is greater or equal to 1 at the frequency where feedback is positive, instability can arise. Poles are at frequencies where T equals -1. In Nyquist plots, each value of S in the S plane has a corresponding value in the T plane. So here's the S plane. Remember, it's sigma on the real axis, j omega on the imaginary, and here's like the right half plane right here. Well, each of these points in S, if you plug it into t, you make a plot in the t plane. So the t plane is like the real part of t, imaginary part of t, and you get this sort of like dome shape right here. Here's t being -1 on the real axis. Okay, if -1 happened to be, if this dome, extended out and included -1, then you would know that your amplifier, that system, is unstable. If -1 is not included in this area, this purple type of area, then it is stable. Okay, so that's what this Nyquist tells you. And it's more qualitative instead of quantitative, but it's a quick way of determining your stability. I'll give you an example of it being inside the dome. In this case, it's inside the dome. So this was done in MATLAB, and see this little, right here, this is like the unit circle, right here. And so here's like t -1, right there. And as you can see here, it's inside, this whole thing right here, it went and looped back around, and so that t being -1 is inside there. So for this system right here, it is unstable. Okay, and that, so tangibly, what that means is that your feedback coming back through beta is, it could be a positive value, like a small positive value, or it could just be larger than 1, such that every time you're feeding back, the system is growing in some type of way. Okay, so that's what's happening here. Okay, so that's our time for today. See you guys later.